Thank you so much for the introduction. Thanks for the invitation. It's been a wonderful workshop so far. Thank you all for coming after lunch, back in time. So I'd like to talk a bit more about control now in this part of the workshop, but in the spirit of it, about optimization-based control. Talk about some of the opportunities, but also some of the challenges that we see. So let me begin with the motivation. I think there's really one key benefit of optimization-based control, and this is that we can get rigorous safety guarantees in addition to achieving a high-performance controller. And here, when I say safety, for the purpose of this talk, we'll think about safety in terms of constraints that we like to satisfy. And this is achieved by leveraging a model of our system dynamics that we use not only to minimize the performance objective, but also to directly impose the constraints. And here we'll be thinking about the state constraints as our safety constraints. And here, this is really just our vanilla optimal control problem that we've written down here. But of course, if we're thinking about this, now we can get rigorous constraint satisfaction guarantees. And I think also in comparison to some other learning methods, we have dynamic feasibility of these trajectories that we're planning with these. Of course, this comes at the cost of having to solve an optimization problem in real time. So whenever we propose a method, it's really important to us that we simultaneously think about how to efficiently implement these things. So it has to come with the right optimization method together. As a result, we're usually not solving this problem, but we tend to solve rather short horizon problems, but we repeatedly solve them in sort of a model predictive control type iteration in order to sort of mitigate this issue of solving these problems in real time. In addition, of course, there's actually lots of uncertainty in this problem when we think about doing this for rather complex control problems in the dynamics, because either we cannot model the full dynamics, we don't know it, it's changing, but also in the environment which we see through the constraints, or in the objective function, which has to usually be a rather simplified surrogate objective in order to solve these problems. So in our work, we take two sides to this picture. On the one hand, we think about how now to get these constraint satisfaction guarantees under uncertainty, which here I term loosely robustness under uncertainty. And on the other hand, how we can reduce the uncertainty by learning more about the unknowns. And it's really about the balance between these two and the interplay that I think we need to manage very well in order to get effective methods that are high performance and with guarantees. So I'd like to tell you a little bit about ideas that we have developed in the group on both sides of these. But before we dive in there, let me just come back to this original definition of safety here for a moment. So I said that by just using a prediction of the dynamics, we can impose directly the constraints. But of course, if we only predict a short horizon forward, then this is not fully true because we want guarantees for all times. We actually need to think about invariance. So we'd like to have ideally an invariant or a control invariant set in which we know we can keep the system so we cannot violate constraints in the future. If we write this in this predictive form, then it's actually not so bad if this is a conservative approximation of some invariant or control invariant set, because we can plan with the trajectory towards it and thereby get constraint satisfaction guarantees. This is, of course, no news for people working in predictive control because that's the entire backbone of it. But interestingly, you can extract that as a principle also to get constraint satisfaction guarantees in other combinations. So people have now used this, for example, in multi-trajectory MPC, where you plan the performance and the safety trajectory. We've used it to run safe exploration methods. Or you could also sort of decouple it from your optimization of a real control problem and think about this more as an additional component. So rather than integrating it into the controller, you can think of this as a component that just verifies if some proposed action can be safe, which is often termed a safety filter. And if you combine this with this predictive idea, then it's literally just changing the objective function to match some other control action if possible. This is, of course, not the only way of how you can write safety filters. You can use Hamilton-Jacobi, reachability type techniques, control barrier functions. They're all related. And if you're interested to read more, you can look at this article in the Control Systems magazine where we've tried to put the things sort of next to each other. But also control barrier functions, of course, in a sense, can be seen as an optimization-based way of certifying constraints, because rather than now having this prediction horizon, you sort of condense it into one decreased condition that you need to verify. And you can connect these two, for example, to approximations of this horizon into a single decreased condition. So unfortunately, I don't have time to talk about this more, but this is sort of how we think about constraints. We think about it as planning a trajectory forwards to some safe set, and I won't be talking about the safety filter perspective for today. But now what do we do if we have uncertainty? Now we need to think about constraint satisfaction under uncertainty. And as was mentioned before, our group has actually now spent, I think, a decade thinking about how we do this rigorously, both thinking about robust methods where you assume sort of bounded disturbances, but also thinking about the stochastic setting where you could have potentially unbounded noise. For both of these directions, what is really key is to find a good balance between rigorous methods and guarantees, as well as computationally effective techniques. And I'd like to sort of briefly show you one variant, which is sort of an online optimization method that we have developed. So let's assume that we have our nonlinear dynamical system and we have some additive bounded uncertainty on it. Now, the fundamental principle of robust constraint satisfaction is that you reduce your planning to a nominal trajectory. You apply a tracking controller to keep your uncertain system close to that. You bound the error between the two, and you can use that for constraint tightening. And that's actually a very similar principle across the robust and the stochastic methods. Now, the conservativeness, of course, comes in when you design your tracking controller beforehand or when you bound this arrow between the two. So an idea is that you'd like to co-optimize all of this to get very sort of constraint tightenings with reduced conservativeness. This is not a new idea. It's actually one that's been discussed 20 years ago in the form of disturbance feedback. So you want to make your control actions a function of the disturbances and then be able to optimize over the feedback. Now, what is new is that we're combining it with some new tools from system level synthesis, which then also allows us to write the state trajectory in parameterized form as the system responds, multiplying the disturbances. So here, keep in mind that we're doing this for the error dynamics. So what we're doing is we're sort of directly representing the closed loop error dynamics now under this tracking controller as with system level synthesis and the system response. What this allows us to do now in the sense of constraint tightening is that we can directly overbound the error once we have bounded disturbance sets to describe where the uncertain system will lie with respect to the nominal one. And here I've written this for the linear system for simplicity first, you can use this to tighten your constraints. So note now that these system responses are also optimized in this optimization problem. So you're optimizing over this feedback, over the error bounds simultaneously and representing the tightening here. This directly generalizes what's been done in robust MPC, also in the linear case, but I think the method really shines when you think about the nonlinear case, where often robust methods introduce a lot of conservatism. Here, what we do is that we actually rewrite our nonlinear system as a nonlinear nominal system, then a linear time-varying error system, plus an overbound, where the linear time-varying error system we could treat with system-level synthesis techniques, and then jointly optimize over all of these terms to get very good overbounds on these errors. Of course, now you might complain that we've just made the problem more complex, right? Now we have these system responses that we're optimizing over. So as I said before, we also need to think about how we optimize these. And this is joint work with Moritz Steele and his group, where we've been thinking about a tailored optimization solver, where we alternate, in a sense, the nominal MPC with the disturbance feedback optimization. And with that, we can actually reduce it to a problem that is not much more expensive than a nominal MPC. So Antoine, who's working on this, has then also complemented this with the recursive feasibility proof. So you can now also run this in a receding horizon. And if you're interested, you can visit him at his poster on Wednesday afternoon, and he can tell you more about this idea. What's really exciting to see is that we get very efficient computation times. We've done it for these sort of smaller scale systems, but recently he's also worked with Glenn Chu from Georgia Tech to extend this and apply it to higher dimensional robotics problems. And also for this, we've extended it to output feedback. And what you can see here is a larger scale humanoid in simulation for which we were able to compute these robust nonlinear solutions in very efficient computation time. So I think what this is showing us that we're sort of close to scaling these things up to full-scale robotics problems. Okay, so now we have an idea of constraint satisfaction, and I've shown you one idea of what we could do when we need this under uncertainty and how we could do effective robustness for nonlinear systems. Now let's think a little bit about the learning side. So as we're thinking about learning in this optimization-based control setup, we'll think about this again in all the levels that we have in our optimization problem. So we'll think about learning that can be used to improve a model of the dynamical system. Think about learning of the constraints in case we do not know them a priori. And we can also think about learning of the objective in order to get a better representation of the short horizon cost to improve the performance. I won't have time to talk about all three today, so I picked two. I'll talk about the dynamics learning and then the objective one, which is some recent ideas that I've been developing. And I'll comment on the constraints as we go through the dynamics. So our group now has spent quite some time thinking about how we can make use of a Gaussian process model in order to improve the description of our dynamics if we have complex effects that we have a hard time modeling with physics-based models. Why a Gaussian process? Because it doesn't need a lot of assumptions on what we're modeling. Basically define the mean function, which is often even zero, and a kernel covariance function, and then you can condition on the data points, and you get a distribution of this function that you had a hard time representing. And we've seen some very nice results in our group, but also other people have applied this, for example, to drone racing. But of course, in the spirit of getting constraint satisfaction, the nice thing is that we can also directly get an uncertainty quantification of the residual uncertainty that we have after using such a Gaussian process model. If you're interested in reading more, so our former postdoc Anna, she's now an assistant professor at Chalmers, she put together a nice review article on Gaussian process-based cautious model learning, if you want to read a little bit more about the details. So in addition to getting this posterior uncertainty, something that has also become quite popular in the field is that by making certain regularity assumptions, you can come up with high probability confidence bounds, so upper and lower bounds on these functions that contain the true function with a certain probability that you can then use in a sort of robust type framework. I'll here talk about the dynamics learning, but just I promise I'd point this out. So you can do similar things when you think about constrained learning. If you don't know the constraint, then you can represent it as a GP, for example, and then do safe exploration by sort of slowly learning more about your constraints. I think we've made significant progress in two directions recently with this GP MPC. One is in the computational direction, and the other is in the theoretical one. The first one, and this is Amon's work, who's here in the audience, is to really think about an efficient implementation. And this is also a collaboration with Moritz Steele and his team, where first we were able to connect this to an approach that they call zero-order approximation, was developed for robust MPC. And we can extend this to DP-MPC to show that we do get feasible solutions, but suboptimal, of course, at convergence. And since then, Amon has worked on putting us together in a package that connects sort of efficient learning-based modeling tools to their solver Akados, which is not limited to the GP, but actually you can also use it to connect your favorite neural network. So I think this is really nice. Feel free to use it and let us know how things go, where you can now sort of seamlessly put these things together and get very efficient implementations. Here's an example for a small-scale racing setup in the lab, where we have the car with uncertain tire friction that's modeled with the GP. And we run this with 100 online data points, so a fixed dictionary of 100 points. Because, of course, the disadvantage of the GPs is that the complexity scales with the number of data points. So here we fixed it. But what you can see is that you can run this very effectively in real time while sort of propagating these uncertainties. Of course, what we didn't like is that fixing of the window and sort of so many other sort of sparse GP methods had similar disadvantages. And so Amon worked with a student, Lars, and they extended this now to a spatiotemporal GP setting, where the nice thing is that we can sort of rewrite the temporal aspect as a Gaussian state space model, and then apply things like recursive Kalman filtering to get very effective constant time updates. So now you do not have to window your data anymore, but you can really just run this through your streaming data. And I think this is a very nice start to thinking about this continual learning and adaptation. The example that you see here is one where we have a time-varying perturbation on the steering. So what is applied to the system is not directly what we plan and compute. And you see in a moment when the perturbation here happens with the nominal MPC, then it deteriorates in performance. If I fast forward a little bit, if we now have the spatiotemporal GP MPC, you can now see again these uncertainty propagations. We do not have a perturbation yet, but when the perturbation happens, then we immediately learn about this because we're just continuously taking in the data, and we are able to maintain the very low lab times and the nice performance of the system. Okay, so I think this is sort of a really an enormous step in making these things effective and applicable in real time. And if you want to talk to Amon, you can visit his poster tomorrow morning in the first poster session and learn more. I promised I'd say a little bit about the theory. So what we usually do when we do these fast GP-MPC solutions is that we work with the linearization-based mean and uncertainty propagation, sort of hidden that under the rug so far. These are successful in practice, but it's hard to come up with safety guarantees for these. On the other hand, we have these ellipsoidal over approximations based on the confidence bounds for which you can get nice guarantees, but they tend to be rather conservative in practice. So I think there's lots of rooms for better trade-offs between the two, many people working on this. I want to show you one idea that I think is sort of appealing because it's based on sampling. So it's rather practical and what people probably would do. So you're thinking about sampling from your GP to get, and what we see is that you can actually get very good approximations of your reachable set. But of course, thinking about this confidence bound, you could first think that you would need an infinite number of samples actually to cover that and to get safety guarantees. However, you can pose the question slightly differently and actually ask the question, well, I need a sample that is close to the unknown function. So how many samples do I need? And that's sort of what Manish worked on. It's work with Andreas Krause at ETH Zurich, where he was able to come up with a sample complexity bound so that we can guarantee with that probability 1 minus delta that we have a sample that's epsilon close to the unknown function. And then now you have this epsilon uncertainty that you need to propagate, which is much better than the full uncertainty spectrum that you had with the confidence bounds. So now you propagate these uncertainties around your sample trajectories to give you the reachable set in which your unknown function can lie. You can directly put this then into your predictive control formulation by now solving it over your samples and tightening the constraints appropriately. We've worked both on the theory of this, and here you can actually see this again running on the race car where we have, I think, about 30 samples running forward. So we worked on the theory, so we can also give closed loop guarantees for this, because the feasibility is a tricky one, but you can also get that. And Aaron has then also worked on a tailored solver for this, which we presented a couple of years ago for sampling-based GP-MPC to also make that run very efficient. All right, before I run out of time, I do want to talk a little bit about this idea of learning about the objective. So what is the idea? As we said at the beginning, we often have to run with very short horizon costs when we run MPC. And that is often hard to design, but it's also difficult to capture a lot of context and additional information that you can get in this objective function that you want to minimize. People have approached this with different methods, auto-tuning, preference-based learning. What I'd like to discuss with a few examples is how we could learn the objective from demonstrations. And again, our key focus here is that we're thinking about constraints. So constraint settings, and we want to learn the objective from demonstrations. We could do this with inverse ideas. So you see a suboptimal demonstration and you have to come up with the objective function. But I don't want to go into more detail. I want to discuss or show you some ideas for very recent things where we're trying to connect some of the powerful learning methods that we have today in order to map, rich context and information into a short horizon objective function that we can then solve with the MPC. And by keeping this optimization problem, we get very nice generalization and we keep the constraints in there, which is really the benefit of doing it this way. The first idea is called zip MPC. So what is it? Well, we assume that if you had a very long horizon to look ahead, then you could take all the information, all the context that you want, and you would be getting the true optimal solution. Now, what you do is you try to imitate that with a short horizon MPC cost. So you're basically learning the cost parameters. It was mentioned before that what people have tried is to learn the terminal cost, right? So here, this is actually a generalization where you're learning all the cost parameters to get a better approximation of this very long horizon behavior. And it works really well. What we've seen in first results with these little race cars here is that we can get performances that are very close to super long horizon MPC solutions while reducing the computation time dramatically. So this is very encouraging, and we're currently thinking about other contexts and modalities that we can put into this framework. The other somewhat classical idea of how you can bring information into a cost function is, of course, through a reference, right? This is a standard idea, right? You pre-compute a reference and you track that with MPC to get the constraint satisfaction behavior in. So here, what we wanted to do is we actually wanted to do that for multimodal situations where you, for example, also have constraints, and therefore we work with the diffusion model. Again, here take this example of autonomous racing. You can think about a space where you're basically flattening out the track. You train your diffusion model, and then you can come up with sort of near time optimal trajectories from that. What's the issue? Well, if you have constraints, then the sample can lead to constraint violation. And even if you did train it with a lot of different constraint configurations, if you see a different one at runtime, right, it's very likely that you're going to violate these constraints. So the idea that Howe had, and this is joint work with Michael Mühlebach from the Max Planck Institute, is that we actually introduce awareness of the constraints through a barrier function, But we do that only at inference time, so that we can directly, sort of when we see the new constraint configuration, we can directly take that into account at inference time and guide the samples away from the constraints. Here's a video where we do this. So the yellow line is the sample from the diffusion model, and you see that how it sort of changes the obstacles and directly sort of we react to it and get an improved reference trajectory that we're then tracking with the predictive controller. And again, you could not compute the time optimal plan in this time that we have to update the trajectory. That would be infeasible. Okay, finally, I'd like to talk about another idea that's sort of pretty obvious and many people have thought about using directly language to design the optimal control problem. So it's very tempting that you could just say to your robot, stack all cubes, and then it would go ahead and execute that command. Well, why would you want to do that with LLMs? Because they're very good at breaking down your complex tasks into subtasks. And actually, I was surprised to see this at the time. It's also very good at coming up with optimal control problems for each of these tasks. So it's actually kind of appealing. However, what's of course a little bit hidden is that you have to train this very carefully with examples for each of these subtasks for this to work. Plus, when you give it a new task, you have no idea if it actually works or if it will sort of do something incorrectly. So we've thought about this problem, and we actually address these challenges in two different ways. One is that we sort of rather, in order to learn these subtasks, we write it as an inverse learning problem, also under constraint, right? So that we can effectively learn the subtasks from demonstrations. The second one is that we assume that there is some structure underlying the robotics task, right? So when you're grasping something, it doesn't change completely from task to task. So we're assuming that there's a mathematical structure, some features that are shared, and parameters that, of course, vary between the tasks. And then we learn a mapping from your language embeddings to these parameters in order to generate the optimization problems to execute the task. But what this allows us to do is to assess subtask similarity if we're seeing a new task, to say, well, are we confident that we can execute this task or not? And then we can reject the task if we're not confident. So this has been a great collaboration between 3 different labs. We also worked with the robotic systems lab at ETH to then bring this first in simulation onto a robot arm, build a pyramid or clean a plate, and then we also brought it to, just for demonstration purposes, that this works onto the real gripper. But I think really it just shows another nice way of using some of these powerful tools to connect it to optimization-based control problems. All right, so this brings me to the end. What I wanted to convey is that optimization-based control is actually a great means, a great foundation to combine sort of problems with strong safety guarantees and high performance. We talked about robustness, so really thinking about safety through planning, and then also robustifying this with these sort of online optimized error mechanisms. And then we talked about learning, Gaussian processes for dynamics learning and NPC. And also, lastly, this idea that we can use a short horizon effective optimization problem and use learning to improve our objective function, our short horizon objective, to bring in all the context, all the information that we can learn with other tools. With that, I'd like to thank you so much for coming and for your attention. Happy to answer your questions.